Okay, welcome back. So we're going to continue with the step 4. So let me share the screen again. Okay, I was just explaining how do we imagine the calibration exercise in the economic model. So once again, the model usually has in this form, right? So there are many equations that connect endogenous variables, exogenous variables, and structural parameters. So these are equilibrium defining equations of the model, first order conditions, constraints, etc. Then the solution means expressing the endogenous variables as functions of exogenous variables and parameters. So again, there are many functions here, right? So y1 would be consumption, y2 would be, I don't know, investment, and so on and so forth. And then calibration means you use some of the values for endogenous variables, some of the values for exogenous variables, the solution of the model, these equations, and all these three eventually allow you to identify at least some of the structural parameters. Okay, I'm going to show you how that plays out in the context of a growth model in a moment. But that's the idea, right? So we have some endogenous variables, values. We have some values for exogenous variables and this model solution. So usually we want to write alpha. So you may imagine we want to write using this, let's say alpha k, some of the parameters, as a function of, if we are lucky, some x variables, some of the x variables and some of the y variables, okay? So that knowing these things and knowing the solution, we know the value of a certain parameter, okay? I will show you that this, of course, also includes identification of some initial values, okay? Because that is usually necessary, and identification of some steady state values, okay? Not all, but some, right? Depending on the complexity of the model, okay? So, the last step, of course, is to run the experiment, right? So now you have the question, you have the theoretical foundations, you have the model economy, and you have the parameter values. Then you simulate basically the model for different types of experiments, right? So sometimes you are interested in changing one of the parameter values. Sometimes you are interested in changing the entire valuation of exogenous parameters. Sometimes you design the policy shift you observe in the data, right? You design the model-based version of it, model counterpart for it. So you understand what would happen in the benchmark case, the case where that represents the reality and in the best case, and then you have the counterfactuals, right? Counterfactual in the sense that it is not reality, but what would happen, right? Typically the computational experiment questions require the use of such counterfactuals, right? So what would happen if government sets the marginal income tax rate at a larger level? What would happen if there would be a particular lump sum transfer that is given to the consumers, so on and so forth, right? These type of things. So each time you run the model, you simulate the model with different inputs, right? So in a sense, you go back to this equation. Okay, now after knowing alphas, right? Let's say after knowing the structure parameters, knowing the initial value. So okay, in a dynamical model, of course, what you would have could be written in this way. If these are control variables and if xt's are the state variables, right? You also have, let's say, this function, and there are again parameters here. Okay, now you have initial values, and knowing alphas, if you know all the alphas, right? So this is a parameter vector. So you have alpha 1 dot 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 alpha k. Okay, you go back to this system. Okay, and by changing certain stuff, you can actually run the experiment, right? So starting with some initial values, uh, you compute yt's, right? So if you have xt's, you compute yt's, and you have xt's, you also compute xt plus 1, then you have yt plus 1, right? So this is a simple forward recursion. Then you have xt plus 2, and you have yt plus 2, and etc. Okay, that goes on depending on the horizon of your model. Okay, so typically there's a model horizon, and you want to simulate the model for that horizon. Couple of things that you should be careful of. One is that so to evaluate the success of your model, you have to look at non-targeted statistics, right? Because some of the data moments if you are doing the calibration exercise, remember you are using the solution of the model and you are using some data moments, right? Suppose that you use y1 and x2 to calibrate alpha 3. Okay, then since you are choosing alpha 3 by using by targeting these moments, or some some correlation or variance or covariance, okay, or expected value of certain stuff, then these are your targeted moments, all right, targeted statistics. So ideally, you should not be using these targeted statistics to evaluate the goodness of fit. Okay, because of course, since you are using these moments to get the value of alpha 3, these are not suitable for evaluating the goodness of fit of the model, right? Because it will be, I mean, if you are using these, of course, the goodness of fit would seem okay. Instead, what you're going to do is to look at non-targeted statistics. Okay, so you are using y1 and x2 to get the value, to calibrate the value of alpha 3, then these are not the things that you should look at when you are evaluating the goodness of fit. You should look at other variables, right? Other stuff that that show whether the model is actually a good representative of the actual economy. So there's also one other thing you should be careful in designing your counterfactual experiments. Sometimes you have, I mean, how do you benchmark different experiments, right? So one example would be, so I have this paper where there is human capital accumulation in the model, and also an R&D technology. Okay, let's say AT plus 1. So there's this human capital production function, okay, and there's also productivity growth in the economy. So what I do in that particular paper, so we're gonna study that paper later on, So you may imagine that, so this paper is about Turkey. So you may imagine in a counterfactual experiment where Turkey is like South Korea, okay, in terms of human capital level in the year 2050, okay? In one set of experiments, I'm designing such counterfactuals, but the problem is that there could be 4 parameters, okay? In my model, there are 4 parameters that would imply this result, okay? 4 different parameters that all imply Turkey and South Korea have the same human capital level in 2050. So obviously, then you have to choose these parameter values by using this as a benchmark, okay? And then I want to also study the total R&D spending, the share of total R&D spending within GDP. In Turkey, it is around 1%, but in the experiment, I have this counterfactual, okay? Suppose that total R&D spending in Turkey is equal to 3% instead of 1%, okay? But once again, there are 2 parameters, okay? 2 parameters that imply that 3% level, okay? So in a sense, I need such benchmarkings for designing different parameters. So it is not okay to say, okay, there is this parameter theta, and I am looking at what would happen if theta is 2 times larger. This doesn't correspond to any benchmark, but instead, what you may imagine that, okay, I'm increasing theta to make Turkey in 2015 like South Korea. So theta, so the increase in theta would be 2.73 theta. Okay, so not just 2 as a made up number, but instead 2.73, just to imply Turkey and South Korea have the same level of human capital in 2050. Okay, so that type of benchmarking is important in designing counterfactual experiments. Otherwise, it is not really comparable. So that's all, right? That's all for the counterfactual experiment. So again, let's remember the steps. First, you have the question. Then you must have some theoretical foundations, and using these theoretical foundations in the third step, you construct a model economy, which means you have a fully parameterized model with utility functions and production functions and decision problems and market structures, of course. And then you calibrate this model economy using some data and the model solution, and finally, you design your experiment and run it, okay? So let's exemplify this whole methodology using a simple model. Okay, so it will be an extremely simple model of human capital accumulation. So time is discrete, okay, and from a demographical point of view, there are 2 overlapping generations. This is a setup you are already familiar with. So there are adults in the economy and then their children. Every adult has a single child. For simplicity, we are assuming away all the complexities about reproduction of humans, you know, men and the women. All of these are simplified. So every child has every adult has a single child, and every child has a single parent. So population is fixed, right? And since population is fixed, we normalize it to 1, so we don't really care about the scale effects. Okay, so what are the endowments in this economy? In this economy, endowments are in 2 forms. One is that each adult has a unit time endowment. Okay, so that will be the labor supply, obviously. And also they have the skills, they have the human capital, right? So each generation has a particular level of human capital that, of course, accumulates in time, right? From generation to generation, people become more skillful. People obtain formal schooling, and they build these skills. Okay. So preferences are also very simple. So there is this logarithmic utility function. Adults care about their consumption. So there's this final good in the economy, and CT denotes the adults' consumption of that final good. And also adults care about their children's human capital. Okay, so each child will have a human capital level of HT plus 1, and alpha here is an altruism parameter because that represents the adults' preferences for their kids, right? So adults obtain utility if their kids are more skillful. Why would that be the case? Well, because adults would want their kids to have better skills, more skills, so that their kids earn more as adults and have a large level of utility. Of course, there are many other ways uh, of studying such models. For instance, you may also imagine this type of a utility function, right? So these are recursive preferences with beta equal to 1. You may write a dynamic program right, a Bellman equation in this form where human capital is the state variable. Okay, but this part, this particular formulation is simpler, and this is sometimes called warm glow preferences. Okay, and it basically allows you to find analytical solutions. Okay. So technologies, so there are two technologies, right? One is the production technology, and here we are assuming that the production function is linear, so there's no physical capital. Okay, there's no physical capital, there's only human capital and raw labor. And theta is some fixed productivity. Okay, so output technology, production technology is this. Now there's also production of human capital, right? And human capital requires education expenditure, right? So this is the human capital production function. Gamma is some again productivity term for education technology, right? So if you spend ET dollars, okay, for your kids' education, and if your human capital level is HT, then your kid would have HT plus 1 units of human capital. Obviously, eta is an elasticity term and it is fixed. Okay. So as you see, it's a very simple model. Now, market structures. Well, we want to assume that the good market is perfectly competitive. So here we assume price is normalized to unity, right? Because this is a general equilibrium model, and eventually one of the markets is going to clear through the Walras law. And there's also the labor market, and we assume the labor market is perfectly competitive as well. So the price of labor is denoted by WT, right? So and the market clearing condition is LT equal 1 because population is equal to 1, remember, right? So if you remember that population is equal to 1 and labor supply per adult is also equal to 1. So total labor supply is just equal to 1 and demand is equal to total supply, which is equal to 1. Okay. Now, of course, here we are interested in public policy. Okay, how education should be financed. Okay, and the idea is this: so government here will impose a lump sum tax. Okay, so it will be a lump sum tax that may change in every period. Okay, which is TT, and then using that particular tax revenue, the government subsidizes education expenditures. Okay, with a subsidy rate sigma, right? And also we assume, again for simplicity, that government has a balanced budget. Okay, so sigma times ET would be the total government expenditure in the form of education subsidy, and TT would be the total government revenue originating from the lump sum tax, right? So how can we write the budget constraint of an adult individual? Well, very simple. There is consumption expenditure, okay? There is education expenditure, and now you see subsidy rate is important, and there is the tax, okay? So all of these spending components should be equal to the wage, right? So there's no asset income, there's no other transfer, okay? So if you solve this model, again, very simple. So this is the utility maximization problem, and this is the profit maximization problem, right? So here in the utility maximization problem, the adult individual makes an optimal choice of consumption and educational spending under these constraints. Okay, so you want to put you want to substitute HT plus 1 here, then you eliminate C from this, and eventually your problem is to choose the optimal education spending. Okay, and here the production function is linear, the cost is also linear in labor, so there's perfect competition, so there's zero profit, etc. And what you learn from the decision problems is that the solution of education spending is this, okay? And profit maximization basically solves the wage in the economy, okay? So what do we have? Well, a certain fraction of income is spent on education, and the subsidy rate increases, of course, this education spending, right? So if you look at this carefully, if subsidy rate is larger, there is a nonlinear effect on education spending, and if human capital is larger, then of course wage is larger, right? Because that's the source of growth in the economy. If human capital is getting larger and larger, wages are getting larger and larger, and consumption, real consumption, is getting larger and larger. Okay. You may define GDP per worker in the economy. GDP per worker is equal to real wage because production function is linear and there's no other input. And you can also calculate the growth rate of GDP per worker, right? So the growth rate of this is exactly equal to the growth rate of human capital, okay? And the growth rate of human capital, so if you solve this equation, I'm taking a couple of shortcuts here, but you had this equation, remember, HT1 minus eta, right? So from this, the growth rate is expressed in this way, right? HT eta. Then HT etas disappear because education depends on human capital as well. So eventually you get this, okay? And once again, subsidy is important for growth rate, right? Because when subsidy is getting larger, education spending is getting larger, and growth rate of human capital is getting larger. Okay. So. Now, parameters to be calibrated. In this model, we have 5 parameters, right? Alpha is the altruism parameter in the utility function. Gamma is the productivity parameter of the human capital technology. Eta is the return to education in the human capital production function technology. Theta is a productivity parameter in the production of aggregate consumption good. And sigma is the subsidy rate. Okay. Here we assume that the initial value is given. Okay, as we always assume. Now, the fundamental question here is this: are all these parameters identified? Now, identification here means that whether I can learn the values of parameters by using the solution of the model, the values for endogenous variables and the values for exogenous variables. So identification in that particular sense means whether I can actually come up with alpha, gamma, eta, theta, and sigma, okay, using data and the model solution. In most models, not all parameters are identified, okay? In most models, not all parameters are identified, and sometimes you can identify them only numerically, okay? So you cannot actually prove, using a closed form solution, you cannot actually prove they're identified, but then you, of course, go to, in your algorithm, you make certain, so you write your algorithm in such a way that, for instance, if you have 5 parameters, and if you are using 5 moment conditions, and if your algorithm works well, always converging to a minimum. So if this is a distance minimization problem, if it always converges to a particular minimum, then you can say, okay, there's joint and exact identification. And sometimes you have 5 parameters, but you are using like 13 data moments, then obviously your parameters are not exactly identified, and you run some further tests on over identification restrictions. But in this simple model, as I will show, we can actually identify some parameters. So let's start with the timing convention. So this is a dynamic model, which means you should be careful with the length of t, okay? Now, this is an OLG setup, which means the length of a period is long, right? Because there's adulthood and there's childhood. So at least we're going to assume something like 25 years, okay? Then I will first look at the subsidy rate, okay? As you see, I have a direct comparison with the data, okay? So I am doing that for the US economy. In 2002, all of the states in the US economy spent about $66 billion on higher education subsidies, okay? Now, if you look at the total post-secondary education in the United States, it is equal to $289 billion, okay, in 2002. So very roughly, we have some idea about sigma in 2002, okay, and it is 23%. And here, of course, I'm assuming, I'm ignoring that this is just for higher education, right? So, of course, it could differ for high school, it could differ for, sorry, it could differ for elementary schooling. But there is at least one type of data that tells me that about one-fourth of education, total education spending in higher education in the US is actually subsidized. Okay. So then that gives me a particular idea about sigma. What I am doing right now? Well, I am using the definitions of the model and using data, right? I'm using data on education subsidies and I'm using data on total education spending, and I calibrate sigma. Okay, so sigma is checked. Then, how do I know theta? Well, that's also very simple. Remember that there's this data source called Penrose tables, right? So in the Penrose tables, you have aggregate GDP, you have population, and you have human capital. Okay. Then what I did is going to 2002 Penrose table. Okay. And I use the production function and the model solution for GDP per worker. Okay. And I realized that theta that is consistent with this data is equal to around 12,000. Okay, so that's a large number because GDP measurement is made at, I don't know, some dollars. So theta is a large number, but be careful. This model is entirely very simple. So there's no physical capital, there's no TFP component. Every single, you know, so growth is entirely depending on the human capital, right? So then there is this particular value of theta, which is equal to 12,763, and that is consistent with 2002 data for the United States economy in the Penrose table. Okay. Once again, I am using very simple logic here. Then things get a little bit more complex. Okay, in the United States, the total expenditure on educational institutions as a percent of GDP is equal to 5.8%. Okay. Now, what is that thing in the model? In the model, income is equal to theta HT, right? Remember that population is equal to 1. So income is equal to theta HT, and education spending is equal to ET. So if you calculate this in the model, this is the expression you get. Okay, so it depends on alpha, eta. So alpha is the altruism parameter. Remember, eta is the returns to education, and sigma is the subsidy. So these three parameters determine the fraction of GDP spent on education. Okay, and in the data, it is equal to 5.8%. Now, what is this? This is an equation with three unknowns. So this is like the G equation I mentioned earlier, right? So this equation, if you look at it carefully, this is a G equation that tells you something about, so this is originating from this equation, right? This is the model solution. It tells you something about the parameters of the model, right? Given data. But the problem is that alpha and eta are not separately identified if you look at it carefully, because these parameters enter this function in this way. And even if I know sigma, remember that I calibrated sigma earlier as equal to 23%, right? So even if I know sigma, and even if I have the data on the GDP share of education spending, I cannot separately calibrate alpha and eta, right? However, I can calibrate alpha eta. So alpha times eta must be around 4.6%. Okay, but I cannot know what alpha is equal to, what eta is equal to. Okay, we have to introduce additional information. Okay, what additional information? Okay, so there are two strategies. Either I'm gonna look at the other studies in the literature that come up with some value of eta, let's say, okay? Sorry, or some value of alpha. So if I know one of them, right? If I know eta, since I know alpha times eta, I can know alpha. If I know alpha, again, since I know alpha eta, I can know eta. Okay? So one strategy is to look at other studies, and guess what? Well, we have this nice study, Delacroix and Gosserias, 2012, and they actually have a value for eta, okay, for developed economies. So if that's true, if you accept this as the true value of eta for the US as well, then you have some idea about what alpha is equal to. Okay, so that's the additional information you have. The second strategy is to check the results for different values of eta. Okay, how can we do that? Well, we know that eta is between 0 and 1. Okay, so that's a simplification. I mean, that's a very nice property that we can exploit, because now I can check the alpha values at different values of eta, right? And for each value of eta, there's a particular value of alpha. Why? Because alpha eta is given, right? Alpha eta is given. So then you can have this type of robustness check. Okay. So there are certain strategies then, if you cannot separately identify all parameters, you can still use, other studies in the literature, and you can still design some robustness checks. Okay, the last parameter is gamma, right? Remember what gamma is. Gamma is the parameter in the human capital production function. So in the human capital production function, you have gamma, ET eta, HT1 minus eta, right? So now I have sigma, I have theta, I have alpha eta, and I can know alpha and eta if I know further information. So the last parameter is gamma, okay? And we calibrate gamma using the growth rate of the economy, right? So we know that in the US, the long run growth rate is around 2% per annum, okay? Now, how do I, be careful, how do I convert this annual rate to 25-year growth rate? Well, that's the formula, right? So the 25-year growth rate, G, will be calculated in this way, right? So annual rate, G annual, plus 1, so that would be the gross growth rate to the power of 25, would give you the gross growth rate 1 plus G, which is equal to 1.64. And then you put all the other things into account, and you calibrate gamma as equal to 5%. Oh, okay, we have less than a minute, sorry. So let's meet at 10:55, okay?